All right, in this next video, we'll talk about discrete I/O handling, and that's kind of my terminology here. But basically, it's going to be start to kind of put the pieces together of how the input that we just talked about, the input devices we talked about and the output devices, how do they kind of get handled inside the PLC? And I'd refer to that back in the discrete input video when I was showing the input card wiring, that the voltage signal comes to the terminal of the PLC card, and then it gets detected by the card as being either an on or off based if it's on a if the voltage is 120 volt AC. If it's a 120 volt AC input card and it detects 120 volts AC at the card, then it considers that as an on. If there's no voltage there, it considers that as an off. So this little video will discuss kind of what happens internally. And if you're not familiar with some of the terminology here in computer science, then we'll define that. If you've taken some computer programming before, or if you know computers or understand the concepts of like binary numbers, then some of this should hopefully be a bit of a refresher for you. But if it's new, then don't worry. We'll kind of define it and just at least explain it in the terms of the PLC. The PLC was born out of microprocessors and from computer science, so there's a lot of holdover, shall we say, from the computer science world. So the concepts of binary numbers and bits, bytes, and words are very much used in the PLC. But to review or to introduce just some of the terminology here. So at the very, at the smallest, the smallest thing is the bit. A bit is just an individual, this is just an individual bit. It's either a 0 or a 1. All right, so therefore discrete inputs pretty much would be considered a bit, right? Because the discrete input only has one value to it. It's one bit. It's either on or off. So we don't need multiple bits per se to indicate a discrete input. We just need one single bit. If it's a 0, it's off. If it's a 1, it's on. But we do tend to organize the bits into different groups, and we can kind of give those different groups some names. So for instance, in the computer science world, if we had a group of 4 bits together, we call that a nibble. Now, that's a term that is not really used that often, especially in our industrial automation space, but it is a true computer science term. So I got 1, 2, 3, 4. I got 4 bits right here grouped together. That makes for a nibble. So in this example, we're looking at 16 bits, right? So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I got 16 bits together here. So if there are 4 bits in a nibble and I got 16 bits here, then I've got 4 nibbles of data, shall we say. But the more common breakpoint, shall we say, is a byte. We've all heard the term bytes, kilobytes, megabytes, gigabytes. So a byte, 1 byte is 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. I got 8 bits here together, and that makes up 1 byte. So 2 nibbles makes up 1 byte. 8 bits make 1 byte. So when you talk about your phone having 64 gigabytes of memory, then every byte is 8 bits. So you can do the math there and figure out how many bits you actually have of memory space in that device of yours. The last organization here, at least on this chart, is a word. So a word is 16 bits. So when we talk about word memory length, we're talking about 16 bits. Now, it's interesting that in the computer science world, we use, megabytes, gigabytes, terabytes now. We never have used like megawords, gigawords, but essentially, 2 bytes make up one word. So if you had a 64 gigabyte phone, then technically that would be 32 gigawords, I guess. Take 64 and divide it in half. Anyway, so that at this point we need to just at least understand that the PLC inputs are going to come in and they're going to look just like this kind of chart right here. So I'm going to have a 1 or a 0 that basically indicates an individual input that is wired to that input card. Now, if you've done any math around computer science classes, then you know that if you've ever done any kind of binary number conversion, we know that binary is what we call a base 2 number. Base 2 meaning there's only two digits or 2 characters in that number base, and the 2 characters are either a 0 or a 1. Now so the numbers you're used to every day of your life that you've been learning since kindergarten and earlier is what we call a base 10 number. Base 10 number is based on 10 digits, 0 being 1, up to 9. And then, when we get to 9, we go 1, 0. When we get to 19, we go 2, 0, right? So we're used to the base 10 system. There are other bases out there that are commonly used in computer science world. There's the base 8, which we call octal, and the base 16, which is hexadecimal. And those numbers are significant. 2, 8, and 16. They're all kind of based on powers of 2. So when we get into the computer science world, we really like powers of 2. But here, if we wanted to take a binary number and convert it back into a decimal number, each digit or each bit in that binary number there has a growing order of magnitude to it. So we're going to always look at the rightmost bit as being what we call the least significant. So this is basically the zeros bucket. And this is the 1s, 2s, 3s, 4s, 5s. And what we mean by that is we're going to take this first one, and this is basically 2 to the power of 0. So if there's a 1 there, we're going to say 1 times 2 to the power of 0. That's how we will get that back into a decimal number, or a base 10 number, essentially. And then this is 2 to the 1, 2 to the 2, 2 to the 3. So the value of this bit in this particular byte of information, right? This is a byte, but the value of this particular 1 here in this fourth bit would be 2 to the 3rd. So 2 to the 3rd is 8, and there's a 1 there. So 1 times 8 is 8. So if this was 0, 0, 0, 1, then this actually would represent the number 8 from binary back to decimal. Now you say, wait, this was the 4th bit, but it's 2 to the 3rd. So again, we're starting with power of 2 to the 0, because 2 to the 1 is 2. 2 to the 0 is 1. So partly why we like to use 0 as a significant number when we're talking about binary and in the microprocessor and PLC world. So even though this is the first bit, this would be represented as 0, 1, 2, 3, 4, 5, 6, 7, 2 to the 7th. All right. It's okay if it's not quite, if you're not familiar with binary conversions and binary numbers, it's okay at this point. We're not going to really, this class isn't about doing binary conversions. It's just helpful to understand that, kind of, again, how we kind of can group these bits together. We can kind of use that to our advantage at times. We can kind of use the properties of binary numbers at times to our advantage in the program. We'll probably get into that later, but at this point, we still kind of keep it fairly straightforward and simple. So how this kind of applies to what we might see, linking the real world to the computer world now, is that basically every one of these input cards is going to be a group of bits, essentially. Now, earlier we were looking at this diagram and we said it was 8 inputs, right? We have 0 through 7. So typically in the PLC world, especially the larger PLCs where they're modular, where you buy the input cards separately, not the micro nanos, but the micro nanos are kind of embedded with IO, and they have some odd numbers to them. But if you're buying a card from like a Control Logics card, they're always going to be kind of based on these powers of 2 as far as the number of points on the card. There'll be an 8-point card, there'll be a 16-point card, and the largest they make would be a 32-point card. Those are all powers of 2, and they're all very significant based on some of the properties of the binary number we're just talking about. So basically, 8-point input card, 8 bits, that's basically a byte of data, right? So that input card is a byte of data. And the way how we map our input card into our memory space of our PLC is we're going to basically look at that as a binary number. So the very first input on this card will get mapped to the very first bit in this case they're showing as a full word, but in this word, right? So our second input will get mapped to the second bit, so on and so forth. And then our 8th input will get mapped into our 8th bit. All right. But again, since it's powers of 2, 2 to the 0, 2 to the 1, 2 to the 3, 4, 5, 6, and then 7, right? 2 to the 7th power. That's again why we have our 0s to 7s here on our labels. So the way how the PLC handles this basically is that we have real world devices with real world voltages wired to them, and when those real world voltages come to this input card, the input card detects the voltage change, and there's a particular threshold. So even though it's a 120 volt AC input card, it might actually trigger at a lower voltage. It might actually trigger around 90 something volts. But once it gets above a certain threshold, it will turn on, and it'll detect it as an on. And when it detects it as an on, it's going to put a 1 in the appropriate bit space based on where that card is. So for me to reference this in the program, I have to understand where these bits are. What's the mapping? We'll call it the mapping. Like, where is this pressure switch is wired to input, labeled 4, but that's input 5, physically 5 on the card. I got to know, well, where in this string of bits do I want to point my program to read the value of that pressure switch state? Is it on or off? So I got to know 0, 1, 2, 3, 4, right? So right now, the pressure switch, this pressure switch is represented as being off. If I was reading the memory space live from the controller based on this right now. Okay, so again, more on this as we get into programming, but just to understand that what's happening in the PLC is we're taking all this information from the field and we're mapping it into this kind of bit memory space, and we just got to know how to properly point to that memory table in order to make sure we're pointing at the right piece of data that correlates back to the real world device in the field. Okay. The output card works exactly the same, but just kind of in reverse. So instead, we're not going to be reading the value of the output card. We're going to be writing the value to the output card, right? Because we're going to be telling the outputs, when do you want to turn on and when do you want to turn off. So we'll consider that as a write. We're going to write the values to the outputs. We're going to read the values from the inputs and write to the outputs. So if we're going to write to the outputs, it's going to basically be, if I were to put a 1 in the bit memory space that correlates to the to the output I want to turn on, that basically will tell that card, okay, I got a 1, turn it on. And it basically fires a transistor that's on that discrete output card itself. There's a transistor on there. It'll turn that transistor on, and power will flow, or voltage and current will flow to the actual output device that's wired to that individual output point. If I have a 0 there, then that basically says I'm off. Don't turn the transistor on. So once again, mapping is important here, because we need to know, like when we want to turn on this heater 1, we got to make sure that we're pointing to the right bit and we're writing the value 1 to the right bit. And if I turn this bit 1 to 1, that will now tell this first output to turn on, and that will now send power to that H1 coil and energize it. Okay, so pretty simple, pretty elegant, but again, as we start programming for real, this will start to maybe click a little more. But just once again, we have to understand that we got to make sure we're pointing to the right memory space in the controller, inside the PLC itself. So just I think the last part of here is just kind of the ladder logic programming, and this is just kind of a little bit of a repeat of the ladder diagram we looked at in the relay logic video. But in the programming world, we're going to again, each one of these contacts in the PLC program will now be linked to a memory space or a bit, right? So we're going to point this contact to a bit. We're going to point this contact to a bit. This normally close will be pointed to a bit. This is 2 parentheses, so to speak, but this kind of represents a coil. So this will be considered an output, right? So so the contacts could kind of be considered as inputs, not always the case. The coils will be considered the outputs. That's not always the case too, but typically, this could be an input from the field, and this is an output to the field, basically. And kind of the last piece of the kind of computer science world is understanding the digital logic aspect of things, and that's basically using the ANDs and the OR gates. So if you're not familiar with some of this terminology, it's pretty straightforward. An AND gate implies that you have to have both inputs. So if A and B were the 2 inputs into this AND gate, and C is the output, so it's kind of read, it's kind of read intuitively. In order to turn C on, I have to have A and B both have to be on in order to turn C on. So if A was off and B was off, then C's off. If A is off and B is on, then C is off. If A is on and B is off, then C is off. But if A is on and B is on, then C is on. So that's the only condition where C can be on, is if A and B are both on, A and B. The other version of this is the OR gate. The OR gate is A or B. If A is on or if B is on, then C will be on. So the only time that the gate is not on now is when A and B are both off. But if A is off and B is on, then on. If A is on and B is off, then on. If both are on, then on. So we kind of use that up here in our ladder diagram, because basically looking at these 2 contacts that are in series with each other would be kind of the same thing as an AND gate. We have to have PB1 and CR1 have to both be on in order to get power to flow across this line here, right? So if power was kind of flowing here, we say, okay, this has to be on, and then this has to be on in order to get power to flow through these two contacts. But then we have a parallel branch here. This C, or this LS1, is in parallel. So that would be considered an OR. So to get power to get to this point, we have two paths here, right? We have A and B, or if C is on, right? So either these two are on or C is on, then I'll get power right here. And then we look at the next point, right? So then this is kind of an and as well too, right? So if C is on, then D has to be passing power, and then I can finally get to my output coil here. So we're going to kind of, once again, as we get into programming some relay logic stuff or some ladder logic stuff, it'll be helpful just to think about it in terms like this, because, as we define a scenario, you have to maybe consider that, right? Like maybe we have to have, two things on in order to turn on the thing, or maybe it's an or condition. So just always go back and think of it in terms of the and the ors, and that will help you maybe in the programming. And that's kind of it for this video. We'll pick up in our next one, and by looking at the analog I/O devices that can be used in our PLCs.